Hello to everyone and welcome to this Teledyne e2v webinar. Right now I'd like to introduce today's presenter, Mark Holdaway. Mark has over 30 years of experience in defining and taking new semiconductor products to market in the high-performance analog world. He previously worked with National Semiconductor, Exynos Technologies, and Intersil. Since 2013, Mark has divided his time between consulting for leading semiconductor manufacturers and working to build his own technical content-focused company. He maintains broad interests across the semiconductor space and has the ability to dig into the engineering detail, yet be able to remain detached and see the strategic implications of technologies. Mark, welcome to today's event. And with that, I'm going to pass things along to you to get us started. So Mark, go right ahead.
A very warm welcome, and thank you for joining this session on space and microprocessors. This is an important category of semiconductor device, one of increasing interest to the space community. So whether your focus is Earth observation, communication systems, space science, or deep space missions, there should be something here of interest for you. Hello, I'm your host, Mark Holdaway, and over the course of the next 45 minutes or so, I want to take you on a short, out-of-this-world exploration. A journey to discover what Teledyne e2v is doing to bring some of the most powerful and complex microprocessor system on chips to market, just in time to bring new levels of data processing and control to the diverse range of complex data processing tasks associated with modern space profiles. Today, we're delivering hundreds of flight models to space programs across the globe, and it's noteworthy that in offering the latest microprocessors, we're delivering new levels of value for money to this industry. Space is a diverse environment, and actors have many interests. A typical sample mission is shown here. This image shows recent Earth imaging from the Australian bushfires. Sydney in the south and Brisbane are both visible. This recent image was captured by the European Space Agency's Sentinel-3 mission, an Earth observation program. We're already seeing valuable results, aiding services around the world to manage and respond to the increasing number of bush and forest fires. Concerningly, 2 years of data from Sentinel-3 indicate a worrying trend in that data, with a surge in observed fires in August, year over year. Certainly, the space market is changing rapidly, partly out of necessity and partly by design. The trends we see here at Teledyne e2v include a push to lower mission profile costs. Consider, for example, that SpaceX claims $1 million will launch 200 kilograms with one of their rideshare missions, and that's truly a modest price point by all accounts. A move to reusability helps impact that cost factor further. Disaggregation of services away from large constellations of satellites to smaller ones helps simultaneously keep costs manageable, but in many cases improves overall mission performance and robustness. As costs falls, increasingly more groups of people are now able to contribute to space exploration, with more national governments, research institutes and private companies becoming involved, driven by a common desire to progress science and commercializing new services. It's a fascinating and compelling environment for curious humans to operate in. It's a world Teledyne e2v is privileged to serve. Within the semiconductor group here at Teledyne e2v, we pride ourselves on providing some of the most advanced semiconductors in the fields including space microprocessors and broadband data converters. We design our own products as well as providing specialist space qualification flows for customer off-the-shelf products. A long history of trust means we have excellent strategic partnerships in place with both customers and vendors alike. In the field of processors, we have a long collaborative history with NXP, supporting up until recently primarily their PowerPC architecture, but as we'll soon see, we're now in the process of introducing a brand new ARM core-based processor. Though some of the names may have changed, Teledyne e2v has built a long heritage serving space, which extends back more than 35 years. Our involvement in countless space missions means we're supplying hundreds of flight models every year. Our value advantage beyond space process flows is an intimate familiarity with all things to do with radiation effects, giving us a solid grounding in this fundamental technical capability. Finally, long-standing strategic relationships makes us a trusted partner across the space industry. Over the next 40 minutes or so, I hope to provide some further insight into our space processor portfolio and details of our space processor manufacturing flows to give you full confidence in our space level expertise. By necessity, I'll only surface this information. Rest assured though, that our commitment to supporting your next space mission is second to none, and qualified personnel are always on hand to help support bespoke product needs. This material is divided into the following topics. What is our processor focus? What do and don't we concentrate on? What makes space components so special? What is our current portfolio and what are the important product specifications? What's the latest news in space processors? This will be especially exciting as we're introducing a new class of ARM Cortex based multi-core 64-bit processors, but more on that soon. How does a supplier like Teledyne e2v de-risk space activities and help improve affordability of components? We'll finish this review with a few further comments on applications and development assistance available from Teledyne. In introducing you to our space processor portfolio, the obvious questions you're likely to have include what are the value advantages of our product offering? Those advantages fall into four main areas as follows. We're a supplier of COTS Plus, customer off-the-shelf products for space level applications. Our processor portfolio enable highly compute and data intensive applications from comms through to image processing. The processor architectures are mainstream, highly affordable, providing programming and reconfigurability capability, and are offered with a wide range of industry standard software development kits available. Furthermore, Teledyne e2v has considerable expertise in responding to the challenges of radiation mitigation in space applications and delivers products across a wide range of internationally defined process standards from COTS Plus and QML all the way to hermetic QMLV grades. Before dipping into product specifics, let's take a look at the challenging environment that space represents. Space is a pretty challenging environment both for man and electronics, as it turns out. Unlike the rather limited range of stresses faced by land-based electronics, space throws in some pretty unusual threats to long-term reliable operation. For instance, no one can view a rocket launch video without a strong sense of the sheer energy creating noise and vibration throughout the whole launch system. This obviously has major implications for the ruggedness of electrical interconnect or wiring. Temperature extremes are to be expected, but their absolute range may not be obvious. In deep space, temperatures reach very close to absolute zero, but around our own planet, temperatures can range easily from 10 degrees to up to around about 120 degrees centigrade. So all of that needs to be taken into account. Another aspect of temperature is what we would call thermal management, and that's particularly interesting in the vacuum of space, as power dissipation becomes largely reliant on radiant transfer rather than conductive as it is back here on planet Earth. Material science and prohibited substances leads us to consider things like the tin solder recipes that we use here on Earth. In the vacuum of space, tin in particular can start to become somewhat fluid, and small whiskers of tin can potentially grow and short between two interconnects. For this reason, space formulations of solders have to be different from the land-based cousins. Heritage means the company has grown foundational skills to enable expert recommendations for the space application of both its own and other companies' products. It's why we have strategic relationships with a number of global semiconductor brands to exclusively qualify their parts for space-level missions. Part of the expertise many organisations lack today is the intimacy with the challenges of space radiation effects, covering both single event effects and total ionising dosage. This is the next topic that we'll consider. Humanity is rather sensitive to its environment. Given how little evidence exists for life beyond our own planet, we should consider ourselves lucky that we live in a Goldilocks zone. But for that zone to exist is rather remarkable. We have specific needs for the atmosphere we breathe, our habitable temperature range, and are fortunate to have a magnetic field that has an invisible but vital task in sustaining life on Earth. Once you get beyond our livable atmosphere, things become rather violent from an electrical perspective. Our closest star is known by scientists to create solar winds. These are streams of high-energy electrons and protons, as well as alpha particles and trace heavy ions. At a distance beyond several solar diameters, solar winds can travel at speeds between 250 and 750 kilometers per second. This solar corona can reach 1,000,000 degrees in temperature. We're fortunately protected by our magnetic field and are usually blissfully ignorant of the solar winds unless we happen to be in the northern climes in winter months and are lucky enough to experience the northern lights. Solar winds combined with cosmic radiation events can have significant impact on electronic systems in the shape of single event effects. The cause of these events can be traced either to the solar winds or other general cosmic radiation. In electronic systems exposed to high energy radiation, both soft or non-destructive hard events can occur. The resultant impact on the electronic systems include the following types of failures. In the case of soft errors, systems can experience single event transients, single event latch-up, single event functional impacts. These are primarily recoverable errors, but they may require a system reset to clear. Examples of non-recoverable single event effects include some forms of single event latch-up and especially single event burnout. For total ionizing dose radiation, the source is the same as with single event effect, i.e. it's cosmic or solar radiation. However, total ionizing dose is a longer-term effect that looks at the cumulated effect of absorbed radiation over time. TID is usually measured in rads, that's radiation absorbed dose. The amount of TID in a specific orbit depends on the orbital altitude orientation and time. TID degrades circuit performance over time. Leakage current increases and voltage offset shifts are not uncommon. Radiation lab testing validates the capability of a particular product in the face of total dose radiation. In many cases, a component's total dose radiation strength is hard to predict, though process mitigation strategies do exist, as do fully rad-hard processes, though these prove costly. So individual component suppliers will have their own approaches to this. However, companies focused on consumer and industrial applications understandably rarely invest in space-ready process technology, hence the need for commercial off-the-shelf capabilities. When it comes to testing device capabilities, two approaches are used today. Most widely used is high dose rate, that's HDR testing. Perhaps unsurprisingly, high dosage testing speeds testing, and with most products the aim, or at least the hope, is to meet between 50 to 100 or 300 K. Lateral PNP transistors, often found in precision analog components, have been demonstrated to be especially badly affected by exposure to low dosage rates. This is described as ELDERS, enhanced low dose rate sensitivity, and thus for such circuits a slower low dosage test may be desired. I want to talk about COTS plus space components now. COTS stands for commercial off the shelf, and in general commercial components off the shelf, although they have the benefit of low cost, are largely unsuitable for space. Simply put, that's because commercial components have rarely been exposed to the extremes that are required of space level operation. The process of qualifying COTS for space applications therefore can make it an expensive business. And this explains why component choices can be somewhat limited in the market. However, an approach receiving increasing focus in the industry is what's called COTS plus. This approach takes COTS components and looks to apply a regime of space qualification tests, which include performing single event effect and total ionizing dose radiation testing to arrive at an excellent product compromise. Its key benefits include access to a broader range of devices and potentially reduced costs, as components need be tested more strictly aligned to the mission profile rather than an international specification system. The use of source controlled drawings, or SCDs, with COTS Plus are commonplace, meaning customer needs are optimally integrated into the product specification itself. This table shows where COTS Plus fits within the component reliability hierarchy. As we move up this hierarchy, quality, reliability and cost increase, all the way to the top of this table where you have QMLV, Class S, full space level components. These components give uncompromising reliability in the space environment. It's here at the highest levels that hermetic and ceramic packages are used. Lower down, the traditional epoxy packaging might well be suitable. So here you'll find enhanced plastic, standard commercial off the shelf, and in the crossover zone, COTS Plus. Sadly, it's the case for processors that as you move up the hierarchy, the performance of these processors falls off. It's perhaps no surprise that most space processors operate in the few hundred megahertz clocking range. Bear in mind the economics of microprocessor development is driven by some particular markets, especially in the areas of data centers, autonomous driving and AI. As a result, the highest performance processors use leading edge process technologies and certainly do not consider using costly radiation hardened processes. Fine line CMOS process geometries simply do not lend themselves to harsh radiation environments. Let's consider the market for space processors for a little bit. Today, by far the majority of devices available for space fall into the microcontroller category, defined here as relatively slow speed processors designed to handle watchdog and control functions. They're the kind of applications that are going to be used in things like remote sensor monitoring or actuation control. And because of their central role in mission critical aspects, these devices must be radiation hardened for a long service life. Unsurprisingly, these functions are not considered desirable when delivered on radiation tolerant processes. Now, some examples of components that fall in this category include a device from Microchip, the SAM71, which is available both in a radiation hardened and a radiation tolerant version. These parts can be clocked at a couple of hundred megahertz, for example. Now, these aren't the applications that Teledyne e2v is focused on. We're focused in the upper left quadrant of applications. These are those that can utilize radiation tolerant products. They're served by modern, ultra-high performance processors, optimized to serve compute-intensive applications with very low power consumption. These are functions that add massive number crunching capability to a mission, increase the onboard smarts, and completely transform mission profiles through reconfigurability over lifetime. Furthermore, these are the functions that can to some extent be shielded from the external environment in thermal and radiation terms, making COTS Plus a highly viable economic approach to component sourcing. And just to restate, Teledyne e2v today is offering GigaHertz class radiation tolerant compute and communication processors to fit this quadrant. In this chart, I want to map out the current market scenario. We've already talked about the microcontroller application. As stated, these are mostly radiation hardened products that operate in the 100 megahertz arena and are used for mainly watchdog applications. If you want high performance number crunching and powerful processing performance, you need to look towards the advanced processor options. And Teledyne e2v currently has a portfolio of 4 key products. Firstly, the P2020, a PowerPC architecture, which is a dual-core product, and a higher performance version, the P5020, also a dual-core processor. Both of these devices are packaged in standard plastic packaging. Slightly higher up on the price performance curve are the PC748 and the PC8548. Both of these devices are single core but come packaged in a ceramic flip chip option. Again, I want to stress that all the components highlighted as advanced processors from Teledyne e2v are radiation tolerant as opposed to radiation hardened components. This chart summarizes the relative number crunching performance of each of these processors in terms of the DMIPS that they achieve. DMIPS is short for dry stone MIPS and is essentially a relatively straightforward way of comparing the overall processor performance between different products. As you can clearly see, the best performance unsurprisingly results from the highest performance processor, here the P5020 dual-core device, which achieves DMIPS score approximately 4 times that of the PC7448. So let's look a little bit more at the COTS plus radiation tolerant product portfolio. The first group of products here comes in standard epoxy packaging. Ruggedized rad tolerant, device selection and lot validation is available. There are 2 parts on offer. Both are dual core microprocessors featuring the PowerPC architecture. They run with clock rates between 1.2 and 1.5 gigahertz. They're based on a 45 nanometer silicon on insulator process technology, and both ECSS and NASA grades of qualification are available. The 2 parts on offer are the P2020 and the P5020, and unsurprisingly the 5020 is the highest performance of those 2 options. When you're looking at more rugged mission profiles, there are a pair of devices available in ceramic flip chip. Again, both based on the PowerPC architecture. This time these are both single core microprocessors. They clock at 1.2 gigahertz and are using 90 nanometer silicon on insulator process technology. And both of these products are available as full QMLY qualification. You may well be interested to learn about the heritage of some of these products. For commercial space level, the P2020, we have been shipping flight models now for in excess of 4 years. These have largely been shipped to the United States of America. One program in particular is a survey satellite in a highly elliptical orbit with a 2-year lifetime. This product is still subject to multiple RFQs at Teledyne today. The higher performance P5020, we have flight models under construction right now. Again, these are targeted primarily to the United States and will be used in manned space activities. And typically here relatively short lifetime demand of 180 days. Going to more payload critical applications where we support full QMLY with our products. The first part is the PC7448. We've been shipping flight models for 2 years now, primarily to the European Union, where parts have been used in meteorological satellites in geostationary orbit, where those satellites have minimum lifetimes of 8.5 years. Again, slightly higher performance PC8548 has clocked up solid flight performance. We've shipped to Asia, the European Union, United States, being used in comm satellites, low Earth orbits, and where typically lifetimes are measured between 10 and 15 years. This slide shows a set of radiation results from either Teledyne e2v's own testing or as sourced from other professional organisations. Note that in the case of single event effect radiation, results are quoted in terms of the linear energy transfer threshold of a device measured in LETs, LET. And it's worth pointing out that devices with a LET value greater than 100 mega electron volts centimeter squared per milligram are considered fully single event effect immune. In the case of the P2020, you'll see that it's tested up to 53 LET. There's no latch up at 63 LET, and the total ionizing dose that we recorded with this part is 100k rad. On the 5020, the more advanced version of this family, the single event upset came in at 14 let. There's no latch up expected, and at this point we only offer total ionizing dose radiation on customer request. For payload critical applications, the PC7448 returned a 62 let result. There's no latch up there, and we also measured the part capable of achieving 100k rad total ionizing dose. And finally, in the case of the PC8548, slightly enhanced single event upset of 86 let, and total ionizing dose comes in at 75k rad. So where will you find our existing processors? Well, they've found their way into many Earth orbits, doing service in a variety of projects covering from low Earth to geostationary orbits. This chart shows the various orbital designations in terms of the orbital diameter. Depending on the orbit location, customers need to be able to evaluate and define their likely radiation tolerance needs associated with the mission profile to ensure reliable long-term device operation. And when I project these images of the various parts, depending on the package and the various radiation ratings, will determine their suitability for operation in any one of these particular orbital spaces. Let's come bang up to date on processor technology, as we're really excited to announce the imminent availability of the first high-performance ARM Cortex quad-core layerscape processor from NXP for space. Today, this represents the most powerful comms-dedicated multi-core processor ready for spaceflight models. When you're about to embark on a space mission and you need high-performance, low-power processing solutions, you now have a new option to consider. And I want to talk a little bit about how we de-risk ARM for your applications. When the desired capabilities for a new space processor are under discussion, the kinds of topics that inform that decision definitely include the following items. Maximizing the absolute number crunching capability as measured in DMIPS, as we've seen previously. Improving or enhancing the SWAP benefits on offer, SWAP being the size, weight and performance that a system can deliver. Power optimization, it's a major aspect of selecting an ARM-based approach. Radiation tolerance for extended operating life, and a supplier with intimate knowledge of space mission profiles. Combining the power performance benefits of the ARM core with the deep space knowledge of Teledyne e2v delivers a solution that de-risks your investment in new technology. Taking a snapshot view of the DMIPS performance of the processor portfolio and family from Teledyne e2v, with the introduction of the LS1046, you can clearly see a better than 3 times improvement in number crunching capability. Quite a significant step forward. Continuing the theme of de-risking ARM for space applications, Teledyne e2v makes life even easier in this respect, as it offers 2 alternative approaches. Firstly, there's the discrete processor chip itself, which is available qualified for space level use as the LS1046-Space. However, if time to market is key, then consider the Cormino variant. This features the LS1046 core, but is combined with functionally optimized 4GB of DDR-RAM in a modularized form factor. This option eliminates the lengthy design loop attempting to optimize the memory layout and particularly the PC traces and their challenging clock timing requirements. Let's consider the DDR challenge a little further. This chart compares 3 generations of memories and highlights how major aspects of implementing DDR stresses design approach even more than past versions. The voltage threshold is down a full 20%. In data rate terms, there's a 2 times speed increase. Furthermore, there are a bunch of new functionalities and capabilities not deployed in previous generations. So the complexity trend continues upwards. In practical terms, the upper table here shows how much each new generation of memory reduces the timing margins, which has direct impact on the precision of the electrical design for such complex memory systems. Up for consideration for anyone wanting to do this for themselves include deciding upon the routing topology, the termination, EMI mitigation, and eliminating any impedance discontinuities. All in all, this is not a job for the faint-hearted. It'll demand careful circuit simulation before committing to a PC design. Furthermore, these high-level needs translate directly into a workbook of 63 tips from NXP advising on implementing best practice design to ensure final success. It seems we cannot overstate the amount of design effort modern DDR memory management systems need. Let's take a look at the nuts and bolts of the new NXP Layerscape comms processor, the LS1046. This block diagram highlights all the key functional blocks of the device. Firstly, the core complex. Highlighted here is the processor core complex, which comprises 4 A72 ARM cores coupled to 2 MB of L2 cache. Next comes the memory control and access acceleration blocks. And now I'm highlighting the sophisticated networking and interface blocks of the system on chip. This includes multiple Ethernet links, SATA and PCI Express controllers. The fourth section highlighted here are the multitude of peripherals, including security blocks, general purpose I/O, UARTs and the JTAG interface sections. And finally, the block I haven't highlighted at the bottom there is the 8-lane 10 GHz SerDes links. Other aspects we've not covered about this processor so far include the core clocking at 1.6 GHz and the inclusion of an on-chip DDR memory manager. The device is offered an extended temperature range, -55 to 125 degrees C operation. It exploits a 780 bump flip chip PBGA package. I should also point out that it has a guaranteed 15-year time in market thanks to Teledyne e2v's very own SLIM program, and more details of that can be found on our website. The LS1046 is bristling with connectivity options, including multiple gigabit Ethernet, 8-lane SerDes up to 10 GHz muxed across controllers that can support 3 PCI Express and a SATA 3.0 interface. There's also 3 USB 3.0 interfaces with integrated PHY on board. And just to recap, Teledyne e2v will offer 2 variants of the device, namely a space qualified chip version and the integrated 4 GB DDR module version for accelerated time to market. The Layerscape processor is all about performance applications and offers several high-value user features to significantly enhance its mission profile. For example, virtualization enables the simultaneous running of multiple operating systems. Acceleration options are on hand to provide fast data access and throughput, and security features are there to ensure hack-free operation. Virtualization allows multiple operating systems to execute simultaneously, as well as enabling multi-level user interactions, for example, supervisor and hypervisor. This happens all while maintaining protected and dedicated memory space per user and per operating system. Acceleration helps keep onboard memory caches preloaded to maximize data throughput and the number crunching capacity. Extensive security features help protect against a variety of attacks, providing for secure booting, intrusion detection, and signed code verification and execution.
The Cormino modular solution, as we've seen previously, eliminates the stress of the DDR memory design. However, its versatility goes beyond that. It offers users standardized modularized hardware infrastructure, which can easily be scaled to deliver higher data throughput. It's covered by Teledyne e2v's SLIM extended lifetime availability guarantee, and overall provides fast time to market and more time in market. At its most complete, the Layerscape processor, and especially the Cormino variant, offers a rich set of customer benefits. Those include highest computing performance, lowest power, smallest footprint, strong reuse capability, a rich and pre-validated software ecosystem, and obsolescence management. More specifically, from the user's perspective, this means customers get to focus on high-level system differentiators and long-term architectural issues, one-time design validation, multi-platform reuse, time-to-market acceleration, software integration, and no burdensome obsolescence issues to deal with. Now I'd like to talk a little bit more about de-risking space processor introductions. In this section, we'll consider some of the benefits derived from choosing trusted industry standard technologies and combining them with a comprehensive support ecosystem.
The benefit of deploying COTS as the baseline product for space is that it provides access to the very latest technologies, albeit ones that are untested for space application. The new LS1046 Layerscape processor is no exception. It's arguably the most powerful data processing and comms platform to have ever been put into space. It represents an optimized high-performance platform. It's offered with a mature development ecosystem. Importantly, the device is power optimized, so making it ideal to cope with the challenges of power in space. And it comes from Teledyne e2v with known heritage in qualifying products for the rigors of space.
So what is required to take a COTS product into space? Well, a solid foundation is built upon the initial space screening activities. This requires that all units are serialized so their source and heritage is fully auditable. Obviously, the starting point for a product is to select one that is specified to operate over an extended temperature range, typically -55 to 125 degrees. It's interesting to note that space applications are specifically exempt from the normal restrictions on hazardous materials, and so non-ROS products work in space. 100% visual inspection is applied to all devices targeting space, with the primary objective to weed out defect-free flight models. And finally, and perhaps most importantly, devices for space are fully statically and dynamically burned in to eliminate any chance of infant mortalities. This then is the baseline material from which Teledyne e2v moves on to build space flight models from. However, this is the start of the process rather than the conclusion. Once we've screened materials, the next steps are to establish the mission profile and assess what specific international or local standards are to be applied. At Teledyne e2v, we support up-screening to a variety of standards, and our COTS Plus program recognises essentially 3 levels of reliability according to the European Cooperation for Space Standardisation, as identified in this graphic. Entry Level 3 specifically targets support for short duration missions or low-cost CubeSat applications. Level 2 is designed for greater robustness and longevity and suits science missions and longer mission profiles. For the ultimate performance, Level 1 is designed to support manned space missions, comms and Earth observation satellites, as well as launch platforms, and offers the most robust flight option.
Let's consider radiation testing for a moment. In this slide, I'll show 3 separate steps that we're in the middle of progressing. There's an initial phase where we take our single event effect tests and perform application tests with a target of meeting 40 megaelectron volts. The initial C report has been available since September. We're moving into a second phase where we now start to work on dynamic tests, and the target for those is 60 megaelectron volts, and we're concentrating on single event functional interrupt mitigation. The final C report will be available in Q2 next year. And finally, with regard to total ionizing dose testing, we have a target of 100K rad, and the testing should be complete by the end of this year.
This chart shows the individual steps taken by Teledyne to arrive at final flight model material. This process divides into 2 separate work packages, WP1 and 2, as shown. By this point in the process, we assume we have good baseline performance from the silicon lots that we've started. During the first work package, shown in the upper chart, Once we commit to producing a particular device and having performed all the baseline screening, we initiate radiation testing. When we know the outcome from this, and assuming that it meets customer mission profile requirements, we're in the position to launch lots from which to build flight models. Individual lots are then dedicated to specific customer programs. At that point they move into work package 2, and this second phase will normally take between 12 and 18 months to complete. So in the last few slides I've highlighted the process steps taken to de-risk and qualify individual ICs. Let's consider the same approach, but this time look at qualifying the Cormino module option. As previously established, this option provides the benefits of both modular design and accelerated time to market, thanks to the pairing of a processor with optimized DDR memory. Beyond that, this solution also benefits from other advantages previously highlighted. That's an extensive development ecosystem, optimized processor performance and power, and a known and proven controlled manufacturing flow. The qualification approach for the module compared with the standalone chip is slightly more complicated, as highlighted here. We have 3 separate work packages to arrive at the final finished flight models. The first of these covers the radiation testing of the standalone memory, the chip itself, and finally the combination of the processor combined with memory on its Cormino substrate. We're now ready to launch lots. The second work package is a new one specific to Cormino, and that is we need to execute dedicated board level tests to ensure the ruggedness of the complete module. The final work package comprises the screening phase, quality conformance inspections prior to final flight models being released to customers. So to summarize this process, there are essentially 4 steps to delivering a Cormino solution. The first is the standalone processor undergoes single event effect and total ionizing dose radiation testing. Then we perform the same testing on the DDR-RAM standalone. The third step, we assemble the module and perform single event effect testing, and then finally the last step includes further single event and proton testing. As mentioned previously, aside from the standard electrical and radiation testing we perform, for Cormino there are a range of board level reliability tests applied. I'm not going to go into that in detail here, although on the right hand side of this slide you can see the main elements of that testing. But essentially these tests divide into tests to evaluate reliability in terms of vibration, mechanical shock, and any effects of air temperature cycling. As we near the end of this session, I'd like to finish by tidying up a few loose ends. Let's take a quick look at the processor support ecosystem and also quickly consider some of the applications that these products are going to find their way into.
This chart maps out the extensive ecosystem available to help you in your development activities based around either the PowerPC or the ARM architectures. The NXP software development kit includes extensive support, so Linux kernels are available, there's a range of network applications, there's also a broad variety of NXP drivers supporting Ethernet, the accelerators, peripherals and platform. Furthermore, there are a number of independent real-time operating system suppliers compatible with these various NXP processors. When necessary, including for development of bootloaders and tools, Teledyne e2v is able to supply specific customized software.
For example applications, I want to quickly review 3 typical space programs where Teledyne e2v technology has a role to play. The first example is the European Space Agency's Sentinel-3. This is the Earth observation satellite that I introduced at the start. It's a relatively new platform being used to measure sea surface levels and temperatures, as well as Earth topological features, and has been busy supplying data over the last few years, providing valuable insights into climate change. The second example is ESA's Quantum satellite, one of the first comms satellites to exploit software-defined radio technology to provide high-capacity, agile communications. Finally, there's a burgeoning level of activity targeted towards low-cost scientific experiments made possible by so-called CubeSat form factor. This is the AMSat FunCube-1 project. It's an exciting amateur radio project that placed a 1U, i.e. 10 by 10 centimetre, sub 1 kilogram CubeSat into low Earth orbit back in 2013 and celebrates its 6th operating anniversary in November 2019. It was designed to transmit telemetry data and is widely used to encourage STEM education. If you're interested, you can check it out further at www.funcube.org.uk. So we've reached the end of the road for this summary of space processors, but before we close, I'd like to summarise the topics we've talked about. Over the course of the last 3/4 of an hour, we've discussed Teledyne e2v's focus on space processors and specifically highlighted what that focus is. As detailed, the company targets high-end, compute-intensive, radiation-tolerant processors, rather than the lower performance microcontrollers used in watchdog applications, those that must be rad-hard. We've considered a handful of challenges of taking semiconductors in space and particularly concentrated some time on understanding the radiation topic. We explored the current portfolio of products, which is focused on the PowerPC architecture. We're now working to launch the most powerful communication processor for space applications in the shape of NXP's Layerscape processor that offers quad ARM A72 cores. This is a processor system on chip with extensive built-in peripherals and communication capabilities and provides diverse communication options and value-add features such as virtualization, acceleration, trust and security. We spent some time looking precisely at how Teledyne e2v helps you de-risk your space projects and considered some of the steps associated with ensuring long life, reliable components that work in the space environment. Finally, we briefly looked at the development ecosystem and discussed some of the typical application use cases for these processors. That was Space and Microprocessors on behalf of Teledyne e2v. Thank you very much for your attention. If you'd like to find out more on this subject, feel free to contact us directly or check out the further details on our website as listed here. Hopefully we've sparked your further interest in these products and we welcome your feedback, questions and suggestions. Thank you once again.
Okay, Mark, thanks so much for that great presentation. Now we're going to wrap things up right there. As Mark mentioned, please feel free to reach out to him with any questions. Mark will get back to you following the webinar. Mark Holdaway, thanks so much for taking the time to be here with all of us today, and we'd like to say a special thank you, of course, to all of our audience members for being part of this webinar event. Take care and have yourselves a great rest of your day.